Hi, my name is Erica Keeley, and today I will be doing a video on the Sallen key filter. Just going through some details about the system. It's a second order system. And today we will be using it as a low pass filter. So first I'll do out the circuit diagram of the circuit. We have the input, which goes into two resistors. This goes into the op amp's non-inverting input. Then we have a capacitor that comes across down here, and that goes straight to ground. So that's our second capacitor. There's another one, but now we have the output of the circuit. So V out goes out here, and the inverting input actually goes straight to back into the output. Then we also have our other capacitor going over between the two resistors over in parallel with the whole system right to the output. So that is C1. So that is our circuit diagram, and the values we're using today for our components are R1 is 27k ohms, R2 is 100 ohms, C1 is 10 microfarads, and C2 is 3.3 nanofarads. These are the values we're using. So next we have the transfer function of the system, which is HS equals, we have a big fraction. So on the numerator we have 1 over R1, C1, R2, C2. And on the denominator we have S squared plus S by 1 over R2 C1 plus 1 over R1 C1. That's the S coefficient, and then we have plus 1 over and then another fraction, which is the same as one on the numerator, R1 C1 by R2 C2. So then when we sub in our values here into the function, we get HS equals 11223344.56 over S squared plus S by 1003.703 plus the same number as the numerator, 11223344.56. That is the transfer function. So next, from the transfer function we can get the frequency response, because HW, the frequency response, equals, is the same as the transfer function when S equals JW, but this is true for this system. For practical systems like this one, so there's a quick note of that. So that means we can rewrite this transfer function as HW equals and I'm gonna write it out with as 1.223344.56 over. So it's j squared, s squared will be j squared w squared, but we know that j squared equals minus 1. So we can just put in then minus w squared plus the s will go to jw by 1003.703 plus 1122.3344.56. So that's our frequency response of our system, and it'll be the same as this, except it's just minus w squared plus jw by all this stuff if you're using different values. So yeah, next we're going to put in the differential equation of our system, which we have here as v in the time domain equals v out of t plus 1 over r2 by c1 plus 1 over r1 c1 by the v out t dt derivative of the output voltage plus d squared, because it is a second order system, so it will have a second order derivative, yeah, dt over dt squared. That is our differential equation. Next we have the gain of the circuit, which is v out over v in, which we have as approximately 2 of our circuit. Next we have the damping ratio, which equals 0.149801, and the natural frequency of our circuit is 527.1727 hertz. 1727.1727 hertz. And also we have the cutoff frequency, for those wondering, was 533.189 hertz. So that is all, just some aspects of our circuit that I did it for us there. Next we'll be going on to a demonstration of the circuit in LT Spice with a step input. Thank you.
And when we created the LT Spice circuit for the Sallen key filter, that's what we need. Voltage source, resistors, capacitors, so I can start connecting some of these up. And also make an op-amp will actually work. That's what we need. 2 batteries. Need to save them. Right. The op-amp we put once I give them. And there's batteries voltage values. And saying that I need to give all the rest of the components values as well. So it's just a hint. Here is micro. There's crosses in there. Ohms. 27k ohms. There's plus and minus 15 volts. And now for the voltage input, I will need to make it a pulse signal. Initial value to 0. So the on value to 0.5. Now normally we set that to 1, but the MATLAB to read in the file properly, it doesn't like it when it goes to 1. With the WOW file, it cuts it off. So it needs to be set to 0.5 to allow MATLAB to read. We have to go to MATLAB properly. 0. Until it's at 1. R is a very small value. Or 0. Have it on for 2 seconds. Previous. Now I'm going to just look at 1 second. So before I go any further, I need to ground these voltages. I should be able to on this and see the circuit, the step response of the circuit. So if I, that's the input line there, and that's the output. I zoom in on that output, you can see it oscillates around once. And before I go on, I will need to quickly output that file to use in MATLAB. So I have the file directory ready to go. Just output that to one of the files on my laptop. And I believe this should just be 15,000. That's just which node to take me.
So here I have a MATLAB window open. So we're going to do the code for our Sallen key filter. Our first step is to read in our result from our LT Spice simulation. So we're going to read in the step response that we got when we put in a unit step input. So step response equals, we're going to use audio read to read in our WAV file, which is called output.wav. Yes, that's the one. And we want to plot this against time, so we're going to make a time array. It starts from 0 and it's going to go for the length of our signal step response -1 because we want to start from the 0 sample, and we're going to divide it by the sampling frequency, and that should be our time domain. So now we're going to plot this by just putting plot the t on the x-axis and step response on the y. So we should see that up here on the right. Yep, so I'm just going to put an x and y label on it now. So x label time seconds and y label of amplitude. So they should come up there now. So yeah, here we have our step response, and if we zoom in a bit, we can see a bit clearer that yeah, it looks like what we get out as our output in LT Spice. So that is as expected. From our step response, we can get our impulse response, and we can get that. We're going to call it impulse response, and when it's equal to the derivative of our step response, so we're going to differentiate step underscore response, and it gives us our impulse response. So from this we can find our frequency response. We're going to call it frequency response. We do this using our Fourier transform, so we're going to get the absolute value of the FFT of our impulse response. Impulse response. We're going to multiply this by 2. This is for scaling purposes, which will make more sense in a few minutes. So the absolute value of FFT, perfect, that will give us frequency response. So yeah, so now we're just going to plot this. So plot frequency response and see what we get out. Yeah, so we get out this figure, this graph here, but we have it in bin numbers on the x-axis. We want it in frequency, so we're going to do an array for a frequency axis, which is going to equal, it's going to start from 0 to the length of our signal, which is called frequency response. We're going to -1, and we're going to divide it by the whole thing by the length of our signal, frequency response, and we're going to multiply that by the sampling frequency. So there we go, frequency axis. So now we're just going to plot again our signal, but against our frequency axis. So frequency axis against frequency response. And x-axis. Yep, now it's in from 0 to 1600. We're going to, since halfway it's mirrored, we're going to limit the x-axis to x-lim from 0 to the sampling frequency divided by 2. And this is why we had to multiply our impulse response by 2 earlier, so that it was at the right proportions for when we half the x-axis. So here we go, it's from 0 to 8000, so we can see how our circuit will change each frequencies. We're going to just put in an X label real quick of frequency in hertz, and a Y label of magnitude of the output. So it's, and there we go. So we can see from our frequency response graph that at around between, I think it's between 300 and 500, definitely at 400 hertz, there will be a big spike. Our frequencies will be amplified greatly at that point, and then after around 500 it's going to start decreasing a lot, and then around 1000 it'll return back to 1600. It'll be back to its usual, it'll be attenuated. So it shows us that it will work as a low pass filter. So now we're going to do the Bode plot for this system, we're going to do, and a bode plot is a semi-log plot, so that's what we're going to use. Semi-log x of, we're going to put the frequency axis on the x-axis, and that's what's going to be in log. And then for a bode plot, we have to have the magnitude in dB, so we're just going to do 20 log 10 of our frequency response, and that'll give us it in dBs, decibels. So 20 log 10, so that should be, yeah, so that gives us up this, looks a bit like a mess over here, but we're more focused on this part, which will, that's at 10, that's at 100, that's at 1000. So yeah, if this is, let's put some labels on it so we know what we're looking at. So X label is frequency in hertz, but obviously it's in logs. And then the Y label is magnitude in decibels. So yeah, so here we have, that's 100 hertz, so that's 2, 3, 4, 5. So yeah, so as we say, around 400 hertz, there's a big spike, a big amplification of the magnitude at that frequency. And then yeah, around, as expected, at 1000, it starts declining a lot. It declines, it's attenuated a lot by 1000 hertz. Perfect, so that looks good. Now we're going to move on to talking about the B and A coefficients of the system and how they relate back to the transfer function. So here we're going to put in the B and A coefficient. So you can get these from the transfer function, but I'm going to show how you can get the transfer function from just the B and A coefficients. So we're going to set B as that. All the values on the numerator of the transfer function are the B coefficients, and the A coefficients correspond to the coefficient on the denominator. So we've got 1, 1003.703, and 1, 2, 3, 4, 4.56. So that should be correct. So those are B and A. So now we're going to make system 1, and it equals the transfer function with our B and A coefficients. B, A. And so we can see now system 1 equals, this is our transfer function. And if you look back from earlier, the one we got when we were doing out our calculations, you can see it. It's the same as our B and A coefficients here, and the same as the one we got earlier. So using this, the system, we can get the step response in the bode plot just from having the transfer function. So if we put in step of system 1, this will give us the step response of the system. And here you can see it looks exactly like the one that we had earlier from using the output that we got from LT Spice. We can also use it to see the bode plot of the system. We can see how it corresponds to the one we just did. So yeah, it looks very similar for the magnitude one. We can double check if we can zoom in or not, but it looks around, if that's frequency in radians, there's a big spike, and then frequencies are amplified and then they're attenuated down here. So that is all the MATLAB code I'll be running through. Thank you.
Here we have the video of the circuit being built for the Sallen filter. So it's the basic design of the resistors capacitors into using a quad op amp to help. Next, we attach the power supply. So it is the positive rail and the negative rail of port of the two supplies to create a ground, and from that ground we then have a positive and negative 10 volts. So from the right we have a positive 10 volts and a negative 10 volts from the left, and we use that ground to ground the circuit, and we attach the ground of the function generator and the oscilloscope to it as well. So there's the outputs to the power supply. But the black wire is the negative 10 volts and the red wire is the positive 10 volts. The positive going into the op amp there and the negative as well. So next I'm going to be detecting the input signal and the supply, which is going through the blue wire, and we're going straight into the 27k resistor we have there. And the green wire is the output of the filter, and all these wires are attached to the oscilloscope and the function generators already. Next we stuck in a series of different signals from the function generator into the circuit. So we first stuck in a signal with a lower frequency than the break. So it is about 400 hertz, and it comes out. It should with a voltage the same as the input, and they're in phase together, or very close to being in phase, which can be seen in the board diagram we have. As signals before, the break frequency should be the same as the input. Next, we stuck in the break frequency, or at least as close as we get to it. That's around 533, 34 hertz. And in this case, it ended up being lower than the input by a very small measurement, and ever slightly out of phase as well, which doesn't quite line up with the board diagram we have, as there should be a small gain. They should be out of phase, but there should be a small gain on the output. The output in this case is also the yellow, while the blue signal is the input. Next we have a frequency above the break. In this case we have about 700 hertz, or 717 hertz, and this one should be just slightly lower than the input thing, and it should be more out of phase than the break, which it is. And finally we went for a frequency much higher than the break, so about 1500 hertz. In this case, the frequency is a fair bit out. They're almost 180 degrees out of phase, I think, and is about almost a volt lower in amplitude, and that's all the signals.